Smile. I think we are alive. Well, good evening, everyone. Welcome to our Cosmic Thursdays. I am your host today, Sinan Du. I am in charge of the Education and Public Outreach Program in the Department of Physics and Astronomy at UC Riverside. I am also the main organizer of this event. We are very grateful that you're all here for this virtual talk. We warmly welcome those newcomers and also excited to see a lot of you returning to our events. So it is my pleasure to introduce our speaker today, Professor Gabriela Canalizo, who is an astronomy professor here at UCR. Professor Canalizo got her PhD from the University of Hawaii in astronomy, after which she worked at the Lawrence Livermore National Lab as a postdoctoral researcher. Afterwards, she joined the UCR astronomy faculty and has been in the department since 2003. Professor Canalizo's research focuses on the centers of galaxies containing supermassive black holes in the near and distant universe, and especially how these supermassive black holes may in turn affect their host galaxies. So in today's lecture, she will be giving a summary of our current understanding of black holes from a scientific perspective, and also discussing popular misconceptions and wishful thinkings about black holes. Finally, I would like to introduce our lovely volunteers today that you can see on our panel. So we have 5 UCR graduate students in astronomy joining us in the live chat today. So they are all senior grad students working in research that's closely related to today's subject matter that we'll be learning about. And they will be earning their PhD in just a year or 2. How exciting. So now I'm gonna let them to quickly introduce themselves. Thomas?
Hello everyone, my name is Thomas Wong, and as Shinan said, I'm a graduate student here at UC Riverside. My research focuses on supermassive black holes, so very much related to this topic today. And also, I also deal with dwarf galaxies and bulgeless galaxies, as well as outflows in those galaxies. And one thing that really kind of captured me in astronomy initially was that space is so vast, and it's a very humbling subject. And so that kind of, when I was very young, I found that super fascinating. And that's kind of what got me into the field in the first place. But anyway, thank you, everyone. Thank you for coming today, and I hope you enjoy.
Thank you, Thomas. Brian, you're next.
Hi, everyone. I just wanted to say how much I'm looking forward to seeing all of your great questions tonight. I got interested in astronomy by attending talks like this, and now I'm close to getting my PhD. And yeah, I'm so excited to see your questions tonight.
Thank you, Brian. What about you, Jared?
Hi, everyone. I'm Jared Gillette. I'm a 5th year, and I look at the brightest galaxies in the universe that are powered by actively growing supermassive black holes. And I was also inspired as a child going to astronomy public talks like this one. And I'll look forward to answering some of your questions in the live chat as they come in. Thank you.
Thank you, Jared. Reza.
Hello, everyone. I'm so happy that maybe a moderator here. Also, I'm similar to Jared, was very inspired by these public talks, and I think I owe these talks because I'm here as a PhD student because of inspiration I got from a public talk like this. So thank you for participating.
Thank you, Reza. And finally, we have Nicole.
Hi, everyone. Welcome to the talk. I am a 3rd-year graduate student here at UCR, and I study the very, very early universe and cosmology just in general. And I got interested in astronomy because I wanted to be a Jedi when I was a little kid. So different from everyone else's. disappointed to say I won't be a Jedi, but I found out space is a lot cooler than I initially thought.
That's very cool. Thank you, Nicole. So all these amazing volunteers will be moderating the live chat today, which you can see on the right-hand side. We welcome all kinds of questions and also encourage you to engage in discussions. Since we have a relatively large group today, so we kindly ask you to be respectful to others. The volunteers will answer most of the questions and also pass the others to the speaker as we go along. All the questions for the speaker will be answered at the end of this lecture. So yeah, without further ado, take it away, Gabby.
Well, hello, everybody. I am very excited to hear that there are so many people from all over the world. So welcome to Riverside, where we are hosting you. And I'm very excited to share a little bit about black holes with you. So let me, while I'm sharing my screen and starting this PowerPoint. So just to tell you a little bit about myself beyond what Sinan so kindly said about me, I was born and raised in Mexico. So I didn't have a lot of exposure to astronomy because it's a relatively small number of astronomers that live in Mexico. But I did get to go to one of these talks when I was about 8 years old, and I was very inspired by it. And ever since, I've always thought that it's really important to, as a scientist that I get to be now, it is very important to share our knowledge with everyone. So again, thank you for coming. Now I get to give back to you guys. And like I said, I will be talking about black holes. So this is a little bit of a very ambitious talk because everybody knows a little bit about black holes, and it's very hard to cover everything in a short amount of time. So I will try to tell you mostly facts, things that we have learned through observations with telescopes. But I will talk a little bit about some of the theory that we have not been able to test yet, but I'm putting that under the category of wishful thinking. I do want to also address a couple of misconceptions. So without further ado, let me start by introducing the main player when we talk about black holes. So black holes, the most important thing about black holes is what we call the force of gravity. Everyone is familiar with gravity, right? This is something that we experience every day. Gravity is the reason why we don't just float off and we're flying around. Gravity is the reason why when you have a ball and you throw it up, it'll come back down, right? Because gravity, anything in the universe that has mass has this attractive force. It's a force that tries to bring things together. Anything that has mass, and by mass, I will be using that word a lot. I just mean stuff, right? Anything that has matter in it will have the force of gravity. The more mass, the more gravity. Also, gravity has to do with distance. The closer you are to the mass, for example, our planet, the greater the force of gravity that you will feel. And like I said, we're used to throwing things up and then seeing them go up for a little while, then they turn around and then they come back down because the force of gravity of our planet will bring them down. However, it is possible to escape our planet. We know that because, like in this graph, you see an astronaut. We have gone to the moon. We have escaped the gravitational field of our planet. And so I want to introduce a concept that is called escape velocity. So escape velocity is basically how fast you need to be going in order to get out of the gravitational pull of an object. So for example, for our planet, the escape velocity is basically the speed with which rockets have to go so that when they go up, they don't just turn around and come back down and crash, right? This escape velocity depends on how much gravity an object has. So for example, here, I have this escape velocity. Here it's in miles per hour. It is different for different planets because different planets have different masses. Jupiter is the most massive planet in our solar system. And in order to get out of the gravitational field of Jupiter, you have to be going, what does it say here? 134,000 miles per hour, much faster than from Earth, because Earth has not quite as strong gravity. So with this in mind, the idea that you need to reach a certain velocity in order to escape the gravitational pull of an object, depending on how much gravity they have. I will define for you black holes. So black hole is just defined as a region of space-time in which gravity is so strong that absolutely nothing can escape it, not even light. Why do I even bring up light? Light is the absolute fastest thing that exists in the universe. Nothing goes faster than light. Light takes some time to travel, right? It's incredibly fast. For light to get from here to the moon, it only takes 1 second, right? Whereas astronauts took months to get there. For light to get from the sun to us, it takes 8 minutes. It's super fast. If we got on an airplane and tried to go to the sun, it would take 17 years. So light is so much faster than anything else. And yet, a black hole is a place that has so much gravity that if you were to have a flashlight and you were standing on a black hole, which you can't, but we'll get to that, and you pointed your flashlight up so that it went, just up. The light from the flashlight would turn around and fall back down because it doesn't go fast enough to escape a black hole. So that's the basic definition of a black hole. Now, a black hole, in some ways, it's nothing special. It's just a lot of mass in a very small amount of space. And in fact, you can actually make a black hole with anything as long as you compress it enough. So I have a little bit of an example here. Let's say that you have the whole Earth with all its mass, with all its buildings and cows and people. So if the Earth is the size that it is, right, the size of Earth, then in order to escape, like we saw in the other slide, you would have to be going at 25,000 miles per hour. But now let's say you take the whole Earth and you compress it, you push it in, you kind of like with bread, imagine a loaf of bread that you compress and you make it very dense. And you make it into the size of the moon. Then the escape velocity goes almost twice as much, 48,000 miles per hour. Now you keep compressing it. You make it smaller and smaller, like the UCR campus, right? Or like the size of a small city. Then you would have to go at 25 million miles per hour. So you keep, this is obviously a crazy exercise, but it's a thought experiment. You take the entire Earth and somehow you manage to squeeze it down to the size of a marble or a pea. And then the escape velocity of that object, that incredibly dense object, would be equal to the speed of light. So at that point, you have turned the entire Earth into a black hole. Why? Because now, if you stand on it, you're not going to be able to get out. If you put light on it, light is not going to be able to get out. It will become what we call a black hole. And here's the thing. Light is the absolute fastest thing in the universe. And according to Einstein, which I have here in cartoon, nothing can go faster than light. Weird things happen, and we don't have time to talk about it right now, but you cannot go faster than the speed of light. Nothing can go faster than light. So therefore, if an object has an escape velocity that is equal or greater than the speed of light, then that becomes a black hole. All right, so in real life, in the universe, how does a black hole form? Well, you need to have a process in nature that can naturally do this crazy thing that I just told you, like compress the earth. Yeah, right. How do you do that? Well, in nature, you will need an object that has a lot of gravity to begin with. And a good one is a high mass stars. So if you know a little bit about stars, they come in all shapes and masses. And our sun tends to be one of the smaller ones, even though it's gigantic and it has a lot of mass. But if a star is about 20 times more massive than our sun, you know, something like that, it'll have similar life to the sun, but it will end differently than our sun will. High mass stars go through life withstanding a lot of gravity because they have a lot of mass. So the force of gravity is incredibly crushing, but they also have a lot of what is called fusion. And this fusion, you know, provides a certain pressure that counterbalances that gravity. At the end of the life of a high mass star, this fusion just peters out. It cannot, you know, it runs out of fuel and it cannot withstand that incredible force of gravity. So at the end of the life of a high mass star, something happens which many of you probably have heard of, which is called a supernova explosion. What happens during a supernova explosion is that the center of this huge star just gives in. It cannot hold the gravity anymore. So the center collapses, and this creates an expansion wave that propels out. So there's two things happening at the same time: an explosion with a lot of its mass going out, but the very center collapses, and it forms what is called a stellar mass black hole. And I'll tell you a little more about them in a second. I wanted to interact a little bit with you and just have a quick poll. So just to clarify, our sun will never explode. It will never become a supernova. It'll have a different type of death. It will never become a black hole. But just for fun, for this poll, let's imagine that in the solar system, you know, the sun with all its planets, let's imagine that the sun was replaced with a black hole that has the exact same mass as the sun. What would happen? And I would like you to interact if you have the ability to write maybe on the comments which letter is the correct one. So the first one, the Earth would slowly start to drift in closer and closer to the black hole, this imaginary black hole. B is the Earth would immediately fall into the black hole. C, black hole would devour all the planets in the solar system. Like all of a sudden it would just go and would swallow all the planets. And D, nothing would happen, but it would get colder because there would be no more sun. So which one is it? And I want to give you a couple of seconds. Unfortunately, we have a time lag so that I can't see your answers right away. But the moderators are going to be looking at the answers that you type in. So just type A, B, C, or D. Which one is the correct answer? And I will give it away. The correct answer is nothing. Nothing would happen. it's kind of crazy, right? You replace the sun with this mysterious object, a black hole, and the Earth would continue to go around its orbit and it wouldn't be bothered at all. Why? Because the motion of the Earth going around the sun is given by the gravity of the sun. A black hole would have the same gravity. The Earth would be at a safe distance from it. It only would be different if the Earth went closer to the black hole. And why would anyone do that, right? If anyone went, if any of the planets went closer to the black hole, then it would experience that extra force of gravity. If it gets close to the point where the escape velocity is close to the speed of light or greater than the speed of light, then it would fall into it. But otherwise, we would be perfectly safe, just very cold, right? Without the sun, we would be very cold. So I just want to mention that because I think there are a lot of myths around there talking about how black holes are just going to devour us, and we will talk in a second about how there is a supermassive black hole in the center of our galaxy. Our galaxy is not in danger. That black hole will be there. It'll be happily existing as long as we don't get close to it, as long as we don't go to the edge, if you will, we will be safe. So black holes are not cosmic vacuum cleaners. All right, so how do we find black holes, right? Black holes cannot be seen directly because we just established that light cannot escape from a black hole. The reason we can see each other is because I can see the light that your image, right, as it travels to my eyes, then that's why I can see you. It's the light that is reflected from the sun and from artificial light, and then it travels to my eyes. That's why I can see you. A black hole, if there's light, if you shine light on the black hole, it'll just eat it. It cannot be reflected. So how do you see a black hole? You cannot see it, but you can see the gravitational effects of a black hole on its surroundings. So it is a little bit like when you can't feel wind, you're inside your house, you look out your window and it's very windy. And you know it's very windy because you can see the leaves that are moving around, even if you're inside your house and you can't feel it. So in the same way, we can sit here very safely far away from black holes and we can't see them, but we can see the stuff that is going around them. So for this reason, they are easiest to find in two specific places. One, when they are close, when they have a pair, another star that is going around them. So the second one is when they are in centers of galaxies. So I will tell you a little more about these two cases. And the second one, by the way, is related to the Nobel Prize that was given last year for physics. So that's what a lot of this talk is going to focus on. All right, so what is called is stellar mass black holes, the ones that are formed when a star explodes and it becomes a supermassive black hole. Sorry, no. I got distracted. When a star explodes and it becomes a stellar mass black hole. So, for us astronomers, we call these the small black holes, even though in terms of mass, they're a lot more massive than our sun, our entire sun. So this one's, the story is basically, a lot of stars are formed in binaries, in pairs. When stars form, usually a lot of stars form at the same time. And typically, they like to hang out around each other. And two of them, with feeling the gravity from each other, will circle around each other. Let's say one of them is very massive, and then it explodes. It becomes a supernova, and the core collapses into a black hole. So what you're going to end up with is the other star, which is still alive, it hasn't exploded, and a black hole. And the star will circle this black hole. As the star is circling the black hole, because they're very close to each other, some of the material from the one will fall into the other. And this is what you're seeing here in these animations. Some of the gas from the star will begin to funnel into the black hole. And so it forms a disk, you know, because it's circling around it, and then eventually it'll fall into the black hole. It'll make the black hole gain some more mass. But as it is circling down, it forms this thing that is called an accretion disk. And the gas is going to go very, very, very fast. So it gets very hot. And it gets so hot that it emits X-rays. So what we as astronomers end up seeing from here, from Earth, is we see a star that is going around nothing, right? Because we can't see the black hole. Even this little accretion disk, it's so small we can't see it. And then we see that there are some X-rays that are coming from very close to the star. So what we do is we measure the velocities. We measure how fast the star is going around, because that star, how fast that star will go will depend on the gravity that it's feeling. If it feels a lot of gravity, it'll go very fast. If it feels a little gravity, it'll go more slowly. This is related, for those of you who are astronomy fans, this is related to Kepler's third law, which relates how fast planets or anything goes around another object and the mass of the object. So anyways, you can ask in the questions if you're curious about that. So anyways, as astronomers, like I said, we look at these stars, we see that they're circling around, and then we use some math, fairly basic math, to calculate what is the mass of this little thing that we don't see. If that mass is more than 3 times the mass of the sun, then we know that it has to be a black hole. Because nothing can be that small and that massive, nothing other than a black hole. This is an example that is dear to me, Cygnus X1. This is an example of one of these binaries that I was telling you about. The star, this big bright star, is the companion that we can see, and it has that little companion with the X-rays. This was the first one to have been discovered. It was, I guess it's been studied since 1964, so that's a long time ago. But it took astronomers a really long time to figure out with a lot of precision these measurements to find out the mass of the black hole and confirm that it was actually a black hole. It is near and dear to me because as an undergrad, this is something that I actually worked on, and this was my very first paper. So this was my very first publication back in a long time ago, 1995. And where we looked at the big star, the HDE 226866, Cygnus X1. And what the paper talks about is actually we were able to see this funneling of gas going from one star to the other and to measure it. An interesting little fact about this object is that Stephen Hawking, which many of you will probably recognize, as well as Kip Thorne, who he's very well known for the movie Interstellar, which deals with black holes, but he's also a physicist and a cosmologist. They had a bet going about this object. Stephen Hawking said, no, it is not a black hole. Kip Thorne said, yes, it is. And it ended up that Kip Thorne won. In 1990, Stephen Hawking had to concede and said, okay, you're right. Anyways, those are what we call the little black holes. So moving on to the next, moving on to the next type of black hole, supermassive black holes. So supermassive black holes are sort of at the other end of the spectrum in the sense that they're so much bigger. They have masses that are equivalent to between 1 million and 1 billion times the mass of the sun. They tend to sit in centers of galaxies, or they always sit in the centers of galaxies. And the way that we detect them is similar, except that we have to look at the motions of material, either stars or gas, as they go around this supermassive black hole. So this is sort of a general picture. You have a big galaxy with a tiny little black hole that you can't see, and it sits right in the middle. And by galaxy, I just mean a big collection of stars that are held together by gravity. So that's what I'm talking about. Now, our Milky Way, and this is probably, this is the main part of the talk, right? Our Milky Way, our galaxy, which is also a spiral galaxy, has a supermassive black hole in the center. And this is something that has been studied with a lot of detail, and pretty much everyone now believes that this is the case. But it was a very difficult measurement to make. And let me try to walk you through why it is so difficult. This is a picture of our Milky Way. We are inside the Milky Way galaxy. And when we look at it, it looks like a pancake, right, in profile. And this supermassive black hole sits in the very center of the galaxy. It is very far away. It is thousands and thousands of light years away from us. And it's a very crowded place with lots of dust and stars. And we have to look through all of that and be able to see individual stars moving around this unseen black hole. And it is something, again, it is very difficult to do. So how did people do this? How did astronomers manage to do this? This is a picture from a person, and I'll talk, I'll beat to the punch or whatever, I forget the expression. Anyways, this is the person, one of the 3 people who got the Nobel Prize last fall. And her name is Andrea Guess. She's a faculty member at the University of California in Los Angeles. And this is a picture of her when she was a brand new faculty member. She might even have been a postdoc, very, very young. And she's working with someone who was my boss at the Lawrence Livermore National Lab, Claire Max. She's the director of the UC observatories. Bruce McIntosh was also my colleague at the National Lab. And what they're doing is they're looking at the galactic center, right? The center of our galaxy. And the goal here is to be able to see individual stars. And yet, when you look at this box, all you see is a blur. You can't see individual stars, so you can't measure velocities of stars. You can't figure out that there's a black hole if you cannot see individual stars. Why can't they? Why can't they see individual stars? Well, turns out when we look at the stars in the universe, when we look at the center of our galaxy, we are seeing light that had to go through an atmosphere. And our atmosphere has air that is bouncing around, right? Like the turbulence. When light comes down from a star, the image of a star gets bounced around again and again, and it forms a big blur, a fuzzy blob. And so that's why it looks all blurry. And we can't escape that unless we, have Hubble Space Telescope, but Hubble didn't even exist back then. I mean, it existed, but it wasn't in orbit yet. So what do we do? And this is what these people were so amazing, especially Dr. Claire Max. They were pioneers in developing this technique called adaptive optics. So what adaptive optics does is this really smart, clever thing where the mirror with, you have a mirror that is deformable. It takes the shape of the turbulence in the atmosphere. And so when the turbulent affected light comes in, you bounce it back with the mirror image, and then it corrects so that you get a perfect, or not perfect, but very, very sharp image. And I'm going to skip this. And then I just want to show you what happened when they apply this technique of adaptive optics to the center of our galaxy. Suddenly, it goes from being a blur to being individual stars that can be tracked as a function of time over months and years. And we can see the motions of those stars at the very center of our galaxy. So this is what these movies are showing here. This is starting in 1992. Andrea Guess and her collaborators at UCLA were observing these stars as they were going around this unseen black hole. Well, they didn't even call it a black hole, right? They're going around some dark object. And you can see how, here's in an animation of the stars, you can see how when the stars get close to this the place where the black hole is, their speeds just increase dramatically. And the reason they increase so much is because they're experiencing the extraordinary force of gravity that the supermassive black hole is exerting. They had a competing team in Germany with Reinhard Genzel, and it was a very friendly competition that they had for 20 years or so. And so in the end, they both won. And last year, they were rewarded with, last year they were rewarded with the Nobel Prize. And both Reinhard Genzel and Andrea Guess. Roger Penrose got the Nobel Prize because of theory that he developed about black holes. I can't emphasize enough how important this discovery was, or this measurement, if you will, because there were many people who were skeptical about the idea that black holes existed. I mean, black holes, if you think about it, it's a crazy thing to think. It's mass that has been infinitely compacted or made small, and it has a huge amount of gravity. They're weird. Not even light can escape, right? So there were many skeptics, but when Andrea Guess and Reinhard Genzel made these measurements, everybody was convinced. And ever since then, we know that we have a supermassive black hole in the center of our galaxy. Let me skip a little because I know I'm running out of time, but this was the first one to be confirmed. But there are so many other galaxies that have also been confirmed to have supermassive black holes. And in the last couple of decades, one of the main discoveries in my area of research, which is supermassive black holes, is that almost every single galaxy that has been looked at has a supermassive black hole in their centers. This is not an obvious thing. Why should it be that every galaxy has a supermassive black hole? Does it mean that when galaxies form, they necessarily form a black hole? Or is it the other way around? Do you need a black hole as a seed in order to form a galaxy? We actually don't have the answers yet. And this is what keeps myself and a lot of our grad students and a lot of other astronomers. It keeps us busy and employed because we are trying to figure out what's that relation between supermassive black holes and their galaxies. So I'll just maybe leave you with this thought that it seems like black holes are not only ubiquitous in the universe, but they also have this relationship with galaxies where the bigger galaxies have bigger black holes and the smaller galaxies have smaller black holes. Until very recently, astronomers thought that dwarf galaxies didn't even have black holes. But in the last very few years, we've been discovering a lot of them. And something very exciting, one of my graduate students is here with us, Thomas, is working on this, which this is a discovery from a couple of years ago, where we found that not only do dwarf galaxies have supermassive black holes, but they are launching these tremendous winds that are clearing the entire galaxy from all the gas that they have. This is very important in the development of a galaxy because a galaxy needs gas to regenerate itself. It needs gas to form new stars. And if a galaxy doesn't have gas anymore, then it cannot form new stars. And it is destined to die, right? Once all the stars in the dwarf galaxy die, then that'll be it. So I think that's probably a good place to stop. I'm sorry that I didn't get to the cool things, but I'll just put it out there in case you have questions. There's wormholes, the possibility of traveling in space and time. And so I will leave it there. And thank you so much for your attention. And I guess I will take a couple of questions, or I will leave it back to Zenan.
Thank you, Gabby. Actually, we have a little bit more time if you want to get into the wormhole. So the event doesn't end until 7:30. And actually, a lot of audience are asking about, as a researcher, what you think about white holes. So that might be a good place to, maybe incorporate some of your wormhole slides and talk about the possibility.
All right, well, thank you very much, Sinan. I got a little confused. I thought I only had until 7:10. All right, back in 2012, a movie came out called Interstellar. Interstellar was, what was special about it is that Kip Thorne, one of the guy that was having a bet with Stephen Hawking, he's an expert on black holes, and he was the advisor for this movie. In this movie, they show the idea of traveling through a wormhole, and it's not the only one. There's so many other movies that talk about black holes and wormholes. So in a nutshell, and I actually don't have a lot of slides for this, but in a nutshell, I'll try to explain it very briefly. A black hole is a region, space-time, a region of space-time where gravity is so strong that nothing can escape. This was something that was predicted by Einstein's equations of general relativity. It is one of the solutions. If you work out all the math and all the equations that Einstein formulated, you will come up with the idea of a black hole. However, there is another solution, a mathematical solution that, you know how when you take a square root, for example, square root of 9, what's the square root of 9? It's 3. Well, it's 3, but it's also minus 3, right? Because minus 3 times minus 3 is also 9. It's the same thing with the equations of general relativity with Einstein. A positive answer to one of his equations is a black hole, but there's also a negative one. And that negative is what is called a white hole. What's a white hole? Well, it would be exactly the opposite of a black hole. It is a region where nothing can fall. There's a region that is only spitting out anything. And so it is possible in the universe of Einstein, where space and time form part of a continuum, and it's flexible, and matter can bend it and can distort it. It is possible in that universe that the universe could be bent onto itself, like it is shown here, and that that it could be ripped by a black hole that is connected to a white hole. And so that's what we call a wormhole. And so the idea is things would fall through a black hole, and then they would come out of a white hole, and it would be in some other place, possibly at some other time. In the movie Interstellar, they actually do this, right? They are in our solar system, they go close to Jupiter, I think, and then they fall through this wormhole and they appear in a completely different galaxy, right? They go to Gargantua, is the name of the black hole that they go to. So do they exist? We don't know. We've never seen them. Just Einstein himself said it, just because the equations predict them, it doesn't mean that they exist. However, Einstein has been right in a huge number of things. And so the possibility remains that this may actually be the case. There's a lot of skepticism. You know, I've read a lot about what different physicists who work on this very thing, they think it would be difficult, like even if they exist, they think wormholes would probably collapse very quickly. And that if you were actually traveling through one, you might get crushed. Or another difficulty is, how do you fall into a black hole without dying? And you know, it's not part of this talk, but as you fall into a black hole, you get stretched by gravity, by tidal forces, and it does something to your body called spaghettification, which means you become a spaghetti, right? Very long and very skinny. And of course that kills you. So how do you get around all these different things? And so the answer is, we have never seen a white hole. It doesn't mean that they don't exist. And it may just be true, and then that would be super cool, because you could go across the universe, you could go to a different time in just about no time, right? Immediately. So it is something I look forward to learning more about as, you know, technology improves. But up until now, this remains fiction. It remains wishful thinking.
Well, thank you, Gabby. That was a very elaborated answer. And I guess now we can move on to answer some of the questions in the chat. There are a lot of great questions. So to start with, Bullrog 92,000 asked, how do you determine the mass of non-binary stellar mass black holes?
The answer is you cannot. There is no way. We don't even know if, we don't even know where they are. We cannot locate them. There have been some experiments that people have tried to do where, I didn't get to talk about this, but gravitation, let me actually just show the, I had this image of a black hole. And just because I wanted to talk about how gravity can bend light. And so when light goes close to a black hole, light gets bent, right? So I have this other video. So the idea is, if you have a black hole that is not in a binary, then the only way you would be able to see it is if maybe some other star or some other source of light went behind it, and you would get to see this pattern, right? Which we call this gravitational lensing, because it's lensing that occurs because of gravity. There have been some experiments where they tried to do this with the halo of our galaxy. They were looking for what is called a massive compact object, compact halo object. And they have had a little bit of success where they do see a few events of gravitational lensing, but it is a very difficult thing to do because you have to get super lucky. You have to be able to see it just at the right time in the right moment, right? So that would be how you would do it. Nobody has been able to determine the mass. You can only have a rough estimate. Thank you for that question.
Well, thank you, Gabby. The next question is from Janine Moore, asking, why is it important to understand black holes?
Why is it important to understand black holes? Great. The main reason is, curiosity. A lot of the things that we know about, a lot of the things that we study about the universe is sort of what makes us human, right? To have a wonder of the universe and the things that are in it. Black holes, we're not going to be eaten by a black hole. We don't have to prepare to be rescued from a black hole. It's not a danger to us. So it doesn't have an immediate human application. However, it may be that this time travel turns out to be right. It may be that we someday can harness its power to do things. But, at this point, this is pure for the sake of knowledge and to enhance our horizons and to learn more about the universe. So thank you for that question.
Great, thank you. Next question from Evan Fields. If white hole existed, wouldn't we see them as abundantly as black ones?
I'm actually not able to answer that question because the reason I can't answer it is because I don't know how a white hole would form. We know how black holes form, or at least some black holes we know, but we don't, so we know how black holes form. I talked about one of the ways. There are other ways I didn't have time to get to, but we don't know how white holes form. So that's why I don't know if they would be just as abundant, or maybe they would be much more rare. So yeah, we don't know.
Yeah, still largely remain fictional for white holes.
That's right.
So next question from Dan Zilagi, asking, because of relativity and time dilation, has enough time passed for even one black hole to actually reach the state of creating a singularity?
Oh, that's a very difficult question. And it is a paradox. So I don't know how to answer this quickly. The answer is I don't know. There are two sides to that answer. The theoretical one, where someone would have to make the calculations, has there been enough time, etc. But the practical side, which is what I do because I'm an observer, right? I do the experimental side. We see them, right? I mean, we don't see the singularities, but we see the black holes. We detect the black holes. And for practical purposes, we think of them as having a singularity in the center and then an event horizon around them. But what your question is great. I mean, and I don't really think anyone has an answer for that.
Yeah, that is totally fair. I guess this is still a field of a lot of open questions that we don't really know, even as astronomers. So here is one quick question from Holy Joseph. What is a primordial black hole?
Okay, so a primordial black hole. This touches on how do supermassive black holes form. So we have let me give you the short answer. The short answer is a primordial black hole is a black hole that is formed in the very early universe as a result of the Big Bang. So a primordial black hole would be, you know, at the end of the Big Bang, you know, the very early eras when there's enough material, some of it would collapse directly without forming a star, without going into anything else, and would collapse into a black hole. So those black holes that are formed during the Big Bang, we call them primordial black holes. So yeah, I think I'll stop there because that's the shorter answer.
Thank you, Gabby. Another question from Spoofed at asking, what point is a black hole able to become a quasar? Very
good. So I do have a slide for that. So a black hole, like I said, black holes are safe as long as you don't get close to them. But if something like a star or a bunch of gas or many stars venture close to the black hole, they will be ripped apart and they will start to funnel into the black hole, more or less like I showed with Cygnus X1. So this accretion disk that forms around the black hole becomes very, very hot. And because it becomes hot, it can emit a lot of light. So it becomes very, very bright. So this is what we call an active galactic nucleus. When a supermassive black hole in the center of a galaxy is accreting or accumulating or getting enough material that it becomes very bright. A quasar is a type of active galactic nucleus. So there's a whole family of what we call AGN, depending on from which angle are you seeing it and how bright they are and how much matter they are accreting. Quasar is like the king of this family. So quasar is the absolute brightest of all of the AGN. This is when this is when a supermassive black hole is accreting a lot of matter, and they actually become brighter than the entire galaxy where they live. So at what point or how can a galaxy become a quasar? For example, our galaxy, the Milky Way, is not a quasar. It is not an AGN. It doesn't have any material going into it, or it has a little bit, but not enough to form an accretion disk. So this is part of actually a lot of the research that I have done. How do you turn a normal galaxy into a quasar? And the answer that I found with a lot of the research that I have done is that you can get this when you have a collision of two galaxies. During a collision of two galaxies, a lot of the gas from either galaxy gets bounced around and it can be funneled into the supermassive black hole or holes that are in the original galaxies. And there is so much stuff going into them that they can become extremely bright and turn into a quasar. So thank you for that question, because it's very related to my research.
Well, thank you, Gabby. And here's the final question tonight from Pachamama Radio, asking, as a computer science major with a huge curiosity in gravity/black holes, what kind of fields or opportunities are out there combining the two?
Oh, the sky is the limit. This is, and in fact, one of our moderators might want to take that on because he works with this. A lot of the, you know, as astronomers, we don't get to sit around and wait for things to happen because, you know, sometimes things take millions of years, billions of years for them, like galaxies colliding. So people who know how to do programming create models, and they have to know physics and they have to know programming. And they can put all the physics into these computer simulations, and then we get to run them and we don't have to wait around right? To see what happens when two galaxies crash, or when the Big Bang happened, or in the case of Nakul, when, you know, in the very early universe, when radiation was ionizing the universe. So you could go into astronomy. I mean, you could get an advanced degree in astronomy, but also there are all kinds of careers where you can be working in a place like JPL, where they will take people in computer science, and they will ask you to help them with the models. And you don't necessarily have to be an astronomer. You have to have astronomy knowledge, physics knowledge, but your skills as a computer scientist will be highly valued.
Great. I really like your answer to that question, Gabby. Well, thank you again for a great presentation. I think now it concludes our lecture today. And I would like to thank you everyone again for joining us tonight. Hopefully you enjoyed the lecture and learned something exciting about black holes. Let's also thank our amazing volunteers who were diligently answering the questions in the live chat. So we will be sending out a survey in a couple days to everyone who registered to collect feedback. The survey is completely anonymous, and we will only be seeing statistical results. Having the evaluation will greatly help us keep running this kind of outreach events. So we would really appreciate your feedback, and you will also get a chance to either sign up for our email list, and that way you will be informed of all our upcoming events, or you could even indicate what kind of astronomy topics that you are interested in hearing about. So finally, I would like to quickly have a plugin for our UCR astronomy page. Let's see, right here, which you can follow us directly on Facebook. So right here, simply type astronomy UC Riverside or at Astro UCR, and you'll find us. Whenever we schedule an upcoming event, we will definitely put it all here, and we'll also share a lot of other resources regarding astronomy and astronomy education. So with that, thanks again, everybody. Thank you for joining us, and wish you have a good night. Bye.